Okay, this presentation is going to be recorded. So the first presenter of this session is Professor Mansa. The title of the presentation, Professor Mansa is from the Department of Mathematics, the University of Burdwan, Parba. And the title of his presentation is a study on some class of generalized enriched F contractions and their applications. So the podium is yours. You can start your presentation, sir.
Okay. Thank you very much for your nice introductions. First of all, I would like to convey my sincere thanks and gratitude to Professor ISQGD for sharing my research work to the honorable and distinguished mathematician, scientist as well. So the time is very short, so that's why I would not like to elaborate anything more. So just we'll go to my topic. So already my title of the talk has already been announced, that a study on some class of generalized enriched F contractions and their applications. So really, it is totally based on the fixed point theory and applications. You know that the fixed point theory is a very important platform in different branches of mathematics that's as widely applicable in different mathematical sciences, namely in chaos and dynamical systems, dynamic programming, optimization, control theory, and various types of the differential equations in solving their solutions, and also as well as the integral differential equation, right? Integral differential equation. So, and also in connection with the homotopy theory, there are lots of applications. So fixed point theory has come into the attention to the researchers prior to 1922. And in 1902, the most celebrated mathematician, actually he's a Polish mathematician, S. Banach. So you know that S. Banach has invented a very important theorem that has been widely applicable in different branches of the mathematical sciences. So what he said, that if X be a complete metric space and T is a contraction mapping, then T has a unique fixed points. That means contraction mappings, suppose T is a self map from a metric space to another metric space to itself, and and if we take any different 2 points, that is X and Y, and they have a image distance, that is Tx and Ty, and also their pre-image distance is Dxy, and these two distances are solely connected that by a constant, that dTx_ty is less or equals to alpha times dxy. That type of the mapping is called the contraction mapping, and where alpha is restricted on that mapping is 0, less than alpha, less than 1. Alpha is strictly less than 1.
Excuse me. Sorry, sir. Excuse me. Okay.
Yes.
Sorry, Dr. Manchu. I think you are not sharing your files.
Yes, actually, I am sharing my just preliminary talks, right? No, I will come later. Okay.
Your slides are not moving. Your slides are
okay. So I'm moving it. Okay.
Yeah, so good. Now it's working.
Okay. So this is the this section. The talk of my lectures is divided into 3 sections. There is introduction and preliminaries, and his recent advancements. There is the generalized rich type enriched F contraction. There's contraction mapping and its generalizations, and already been discovered prior to my invention, right? And in this connection, we have established common fixed point theorems, and with the application for such type of the mapping, there is enriched Cannon type mapping, okay, and widely applicable to different branches, namely the Volterra type integral equations, like that. And what is their future works, and in which connection this type of this fixed point theorem are applicable. So that's why I am very much interested to show their applications, right? So namely, it is my abstract. The talk introduces various classes of the possibly non-continuous mapping. Because in the nature, there are so many phenomena coming into our considerations. There is the non-linear mapping, linear mapping. So, but we are not interested to the linear mapping. So many types of the mappings come into play in the natural phenomena. So that's why we are dealing with the non-linear, and not only that, they are continuous. So we are dealing with the non-continuous contractive mappings. That is, the image distances and the pre-image distances are so related, that is the dtxty less or equals to alpha times dxy. This type of the mapping is the contraction. Then after that, Edelstein has developed, there is the contractive mapping, and after that, non-expansive mapping. So contraction mapping implies contractive mapping, then contractive mapping implies non-expansive mapping. But but reverse inclusion is not true always. So that's why I am telling that the talk introduces the various classes of possibly non-continuous contractive mappings termed as generalized enriched F-contractions. So first of all, contraction mappings were developed, then F-contraction were developed, and after that we have dealt with the enriched F-contractions. So that's why I am very much interested to talk with such title. So numerous fixed point and common fixed point theorems for these classes have been proved, supported with several non-trivial examples, illustrating that these mappings may be discontinuous at the fixed point. So it is a very crucial point that the mappings are dealt with the discontinuous type. So furthermore, the applicability of these findings have been demonstrated to solve the Volterra type integral equations and related systems, exhibiting the theoretical significance and their practical relevance in such type of the nonlinear mappings. So we know that the metric fixed point theory is a very vibrant areas of mathematics that already been discussed just prior to my main discussions, and already I have dealt what type of the applications are behind it. So initially, the Polish mathematician S. Banach has dealt with the mapping, contraction mapping. After that, various mathematicians coming to do research work, further extensions. So generally, metric fixed point theory or metric fixed point theory and applications are dealt with the various types of the spaces and also various classes of the mapping. So that mappings may be restricted, that may be extended, and on also the combinations of the different types of the spaces as well as their nature of the mappings, right? So in this connection, so notably mathematicians have done their research work. Namely, Karnan is an Indian mathematician, and Rich, Chatterjee, Boyd and Wang, Hari Rogers, and many others. So you can see there are more than 250 mappings have already been discussed, and that have been stated in in the paper, in the journal and proceedings of American Mathematical Society. You can see in 1932 that by S. Brower, by B. Rhodes, right? So but we have been highlighted, we have been motivated by the works of the Wardowski that has been referred in my reference list. So Wardowski introduced a new class of contractions using the mappings from non-negative reals to the reals, and he called F-contractions and proved some fixed point theorems on it. So these type of mappings are such type of the mappings. What is the definitions of such type of the mapping? That is, F must be strictly increasing, and for each sequence, alpha n of positive numbers with alpha n tends to 0, if and only limit n tends to infinity, f of alpha n equal to minus infinity, right? So and also there exists a constant k belongs to 0, 1, such the limit alpha tends to 0, alpha to the k f alpha is equal to 0. So this type of the mappings are generally denoted by curly f, and the mapping satisfies number 1, F1, F2, F3. So in this connection, Wardowski has introduced a mapping. That mapping is called the F-contraction. So and he invented the mapping. He discovered this mapping on a metric space, and let XD be a metric space. A mapping T is said to be F-contraction if there exists tau greater than 0 and F belongs to curly F. That curly F is the collection of all such mappings satisfying F1, F2, F3, for which tau plus f of dtx dy less or equals to f dxy for all xy belongs to x with tx not equal to ty. So in this connection, he established a fixed point theorem, and that fixed point theorem is that if T is a F contraction that already been discussed in the earlier slide, then it has a unique fixed points. And for every x naught belonging to x, the sequence t to the power n x naught is a convergent to x star, and t to the power n x naught is called the Picard iteration. That means if we start from a x naught, then x1 equal to t1 x naught, and then x2 is equal to t square x naught, and continuing in this process, we can get a sequence then t to the power n x naught. And similarly, we can define that is a F Carnot mapping. Actually, in the metric space Carnot, R Carnot had initiated a mapping that is if XD is a metric space and T is said to be a Carnot mapping if dTx ty less or equals to beta times dxtx plus dyty for all xy belongs to a x, and where beta is strictly less than half. So on the motivation of the work of the Carnot, that is the Batra has introduced a F Carnot map, and that F Carnot map, that is F satisfies that type of the conditions. It is F1 to F3. What is that? Now there is if we take x and y, where x not equal to y and tx not equal to ty imply tx not equal to x or ty not equal to y, and there exists tau greater than 0, such that tau plus f of dtx to ay less or equals to f dxts plus dyty by 2 for all xy belonging to x. So this is called a F Carnot map. And if we deal with the complete metric space, if suppose XD is a complete metric space, that means every Cauchy sequence is convergent to an element, and T is a F Carnot map, then T possesses a unique fixed point. And after that, Barnard has introduced a mapping that is called a enriched contraction. That if X is a nonlinear space, and the mapping T is said to be enriched contraction if there exists B belongs to 0 infinity and theta belongs to 0, B plus 1, that is the left closed and right open, such that B of norm of B of x minus y plus tx minus ty less or equals to theta into norm of x minus y for all x y belongs to X. This type of the mappings are dealt in a nonlinear space. In this connection, there is the Barnard and Pequot has established a theorem that if X is a Banach space, there is a complete nonlinear space, and T is a enriched contraction, then T has a fixed point, right? That is the collection. Fixed T means the collection of all fixed points of T, and it is the unique fixed point. And there exists lambda belonging to 0, 1, such that the iterative scheme xn defined by xn plus 1 equal to 1 minus lambda into xn plus lambda into txn. So this type of the sequence generated starting from the x naught is called the Krasnodar type sequence, and the iteration is called the Krasnodar iteration, or sometimes we say that the Krasnodar scheme. And this type of the sequence generated from the Krasnodar scheme converges to the point with a P, and we can estimate by numerically that that norm of xn plus n xn plus I minus 1 minus P, that P is the fixed point of the T, is less or equals to c to the power T but divided by 1 minus c into norm of xn minus xn. So this is the prior estimation, that is the pre-estimation of the error calculation. So where c equal to theta times theta by b plus 1, and this is called the, already I have told that the iteration scheme is called the Krasnodar iteration scheme. Now, if we define a map T lambda x to x by T lambda x equal to 1 minus lambda x plus lambda into Tx, and where lambda lies between 0 to 1, then it is called the average mapping. And in this connection, there is a mapping is also a Carnot type map. That is the Carnot type mapping. So let X be already I have discussed that the enriched F contraction. Now I am telling enriched F Carnot mapping. So X be a nonlinear space. Enriched Carnot, that a mapping Tx will be said enriched Carnot mapping if there exists beta belongs to 0 half and B belongs to 0 infinity, such that B of x minus y plus Ts minus Ty less or equals to B x minus Ts plus y minus Ty for all x comma y belonging to x. But one can raise a question, what is the difference between the Carnot mapping and the contraction mapping? So naturally they are very independent to each other. So naturally contraction mappings are the continuous mapping, and this type of the Carnot mappings are discontinuous mappings. So so it can be shown by numerous examples, and that's why I am telling and I am motivated with their works also. So in this connection, that is the if T is a enriched Carnot mapping and X is a Banach space, like that previous type of the enriched contraction, we can get a same fixed point theorem, but a little bit construction is there. So T has a unique fixed point, and by Casson's iterative scheme, the sequence converges to the point P, and the same following estimation, that is the error calculation, error estimation, can be found in this iteration scheme by this condition 3. So in 2022, these are the very recent works. Debnath had introduced an updated and generalized version of the Carnot and Rich type mappings using the F contraction given by the Wardowski, and proved the fixed point theorem. So already we have mentioned that is the F contraction, F Carnot mapping. Already we have mentioned that the enriched Carnot mapping, that is the enriched contraction mapping, and now right now the punching the Carnot type mapping or contraction mapping with the F type, and we generally call it enriched F contraction, and generally we call enriched Carnot mapping. So exhibit a matrix space, a mapping T except to generalized Carnot type F contraction if there exists two constants 0 less than alpha comma beta less than 1 with alpha plus beta less than 1 and tau is sum greater than 0, and for some F belongs to curly F, that curly F is the collection of all such mappings F1 satisfying F1 to F3 that have already been discussed, and tau plus F dtxy less or equals to alpha times F dxdx plus beta times d F dy. This is a map. This is called a generalized Carnot type F contraction, and in this connection we can get a fixed point theorem. That's why I have stated this theorem by 10. Let XD be a complete metric space and T is a generalized Carnot type F contraction, then T admits a unique fixed points. Now, another type of the enriched F contraction, that if for some F belongs to curly F, there exists beta b greater than 0 and tau greater than 0, such that for all xy belongs to X, and this condition holds. In this connection, we also get a theorem that X is a Banach space, T is a enriched F contraction, then T admits a unique fixed point, and also by the by Casson's iterative scheme, this sequence converges to the fixed point of the T. So these are the earlier works. So we have been motivated by such works, and we are coming later that what we have done. So in this connection, enriched F Carnot mapping. So if we define enriched F Carnot mapping, then we can get a unique fixed points on a Banach space. So motivated. So that's why this is I am coming into the main results. So motivated by this advancement, we introduce some new classes of generalized enriched F contraction, namely generalized rich type enriched F contraction. That means it includes all such contractions and Carnot type F contractions. So that's why we are calling it generalized rich type enriched F contractions, and prove some fixed points as well as the common fixed point theorems relating to them. And in this connection, we have given several non-trivial examples to support the theorems, and as well as the practical applications in solving the solution of the Volterra type nonlinear integral equations, right? So now this is our definitions. There is the generalized rich type enriched M contraction. X be a nonlinear space, C be a closed subset of X, then the mapping is said to be generalized rich type enriched F contraction if there exists suitable scalars alpha, beta, gamma greater or equals to 0 with alpha plus beta plus gamma less than 1, and B is greater or equals to 0, and tau is some positive real number, and there is some F belongs to curly F. That curly F satisfies the conditions F1 to F3, and this condition also satisfied. So this is called the generalized rich type enriched M contraction. In this connection, we get a fixed point theorem that let X be a Banach space and C be a closed convex subset of X, then a generalized rich type enriched F contraction that have been shown in the earlier slides, that T has a fixed point in C. So in particular, if we take B equal to 0, then earlier works can be found. So that's why it has been shown as a corollary. The above corollary 19 is generalized as the fixed point theorem given by the Debnath. And what Debnath had done, so that has already been discussed, so this is our generalized enriched rich type mapping that includes all earlier work. Right.
Yeah. Okay. I have a question.
Yes.
Okay,
We have
so you mentioned.
question and
Okay.
answer time after the presentation.
Okay.
We'll follow that modality. Yeah. Sorry, Dr.
Okay.
Bilal.
Okay. So I'm ready to answer your questions. So after my finishing my lecture, so I will give you answer. Okay. So so in this connection, this is an example. So suppose X is a space of the real numbers and C is the 0, 1, that is the C01, that is the collection of all real. C is the closed interval 0, 1 and T is a mapping from C to C, that Tx is equal to this, that at the point X equal to 0 and 0 to half, X plus half, and half to 1, this is a discontinuous mapping. So here you see that is the T is not continuous. So it is not an F contraction. We know that every contraction mapping is a F contraction mapping, but the converse is not true. So this is an example, right? So if we take X is equal to 0 and Y equal to 1, then we see that T is not a rich type contractive. So this is an example of the rich type contractive mapping. Again, we see by numerical calculation, we can see that for X equal to 0.45 and Y equal to 0.55, and if we take F is a function, that is the F-type mapping. So there are so many F-type mappings already you have seen. That is the F is a increasing mapping. There exists a sequence alpha limit alpha n, that is limit n tends to alpha n equal to 0 and limit n tends to infinity F of alpha n equal to minus infinity, and there exists a k such that limit alpha tends to 0 alpha per k if alpha equal to 0. So in this connection, there are so many examples of the F mapping. That is fu equal to log u, f is equal to log u plus u. There are so many mappings. So if we take f of u equal to log u, then this type of the mapping satisfies the conditions f1 to f3. So if we take a suitable constant alpha equal to beta equal to 1 by 5 and gamma equal to 1 by 10, then we can see that T is not a generalized rich type F contraction. This is an example that for this such type particular value, T is not generalized rich type contraction. But for tau equal to 0.1 and B equal to 1 and alpha beta equal to 1 by 5 and gamma equal to 1 by 10, then T satisfies the condition, that is the generalized rich type conditions. So T has also a fixed point 0. That is at the point X equal to 0, T0 equal to 0. This is the assumptions stated in the generalized rich type condition are sufficient but not necessary. So this is an example in support of that theorems. So if we take X equal to 1 and C equal to 0, 1, and if we define a mapping S like this, then we see that S is not a mapping satisfying the condition 13, but it has a unit fixed point, that is X equal to 0, right? So these conditions assumed in the statements are sufficient but not necessary. So I am not giving the details. So there are so many corollaries, so many remarks can be found. All the earlier works can be found with this statement. So I am not skipping. I'm not giving in detail. So I'm skipping it. So what is the application behind of such theorems? So if we take the Volta type integral equation, that is this, then we can find out the solutions by this theorem. So what is this? Now, suppose k is a function from 0 lambda to 0 lambda from the closed interval in the space of the reals with usual norm, and k is a function, and q is also a function continuous. K is a function which is continuous, q is also a function continuous, and there exists tau belongs to 1, infinity, and satisfying this condition, then we can get a solution of such integration. Right, so this is the Volta type integral equation. Thus, the integral equation has a solution. So another type of the theorem, there is the common fixed point. What we say, suppose T is a mapping from X to X and S is a mapping from X to S, then there is a unique fixed points. There is common fixed point, that is Tx is equal to X and Sx equal to X. So that is Tx equal to Sx equal to X. So in this connection, we also have been able to find out, to establish a common fixed point theorem. So X is a Banach space, C be a closed convex subset of X, and TS is a two mapping satisfying this condition. Then T and S have a common fixed point in C. So in this connection,
you have 2 minutes. 2
yes.
minutes.
So this is an example of the mapping T and X, and we can see that T and S have a common fixed point 0. And this is the applications. This is an application. If we deal with the two types of integral, phi and psi, then we can get a unique solution of such by the such theorems. So this is the motivation of my research work. And also, this is the common fixed point applications. K1 and K2 are two functions, and Q is also continuous. K1 and K2 are also continuous, and satisfying this condition, then we can get a integral solution. So this is the motivation, and future research may focus on developing multi-valued on-set valued analogous of the present results, such as the fractional differential equation, integral differential equations. Okay, so right now the researchers on fixed point theory are doing on such type of the platform. So that I am very much interested to highlight on our works. So I now stop here. Okay. So is there any question? So
Thank
so
you
this is
so
my
much.
reference. So this is my
Yeah.
reference. This is my reference. Okay.
Thank you so
Now,
much for the nice. Yeah. Thank you so much for the nice presentation. Now I'll stop the recording.